So, good afternoon, everyone. In this lecture, we are going to discuss about depreciation in power plants, and the subject name is power generation process. So, these are the learning objective to introduce students to the basic theory of power generation process and familiarize students to the principle of operation, optimization, and depreciation. So after this lecture, I'm expecting from students that student will be able to understand the uh, concept of depreciation and optimization in power plants. So let's come to the point. With the point is what is depreciation? So rates of depreciation should be adequate to provide resources for replacements of assets after their useful life and accordingly. So, existing provisions for the Income Tax Act, the Companies Act, and the Electricity Act envisage accelerated recovery of depreciation over a much shorter period than the economic lives of the assets. So, keeping in view the requirement of resources for the power sector, government of India had increased rates of depreciation in March 1994. So these rates of depreciation were uniformly applicable to all power utilities, including generating companies, SEBs, and IPPs and licenses. So these increasing depreciation cost, it increased the cost of electricity. So in the last 7 to 8 years, required investments could not be made in the power sector as a result of which requirement of resources for capacity addition and R&M work has increased. So the reduced rate of depreciation stipulated by the Commission will result in reduction in internal resources of all power utilities in the country, including central generating companies and state electricity boards. So this will adversely affect the capacity addition program in the power sector. So furthermore, loans available are of lower tenure 7 to 8 years. And rates of depreciation along with advanced depreciation should be adequate to facilitate loan repayments. Present rates of depreciation along with the advanced depreciation are not adequate and entire ROE during initial 7 to 8 years will have to be used for loan repayment and investors will not be able to distribute any dividend during this period. So such an investment propositions will not be acceptable to any investor. So accelerated recovery of depreciation will help power utilities in mobilizing resources from the existing capabilities for capacity addition. So rate of depreciation as modified by GOI wide notification dated 29/3 1994 may be continued at least for the coming 10 years. So, with the enactment of Electricity Act 2003, Act has been repealed and now all power sector companies will have to comply with the Companies Act and provide depreciation in the books of accounts as per Schedule XIV. So, in the tariff structure prevailing in the power sector, it has been the practice to provide uniform rates of depreciation for the purpose of tariff and accounts. In view of this, alternatively, rates of depreciation for tariff may be prescribed as per companies act along with advance against depreciation to facilitate repayment of loans. So, actually, the electricity cost depends on various factors, and one of them is your depreciation also. So there are some rules and some, you know, some acts which must be used in a power plant to see the to considering the electricity cost. So there are many kind of tariff structure we have already discussed in our previous lecture. Two-part tariff structure has been designed to share the benefits of higher performance with the beneficiary. This is the graph demand versus your fixed charges, including incentives. So, there are some fixed charges which you have to pay if you are paying the electricity bill. So, you can see this tariff structure in your electricity bill where there are some few charges which is fixed if you are using electricity or not, but there are some few charges which is fixed. Okay, so you have to pay those charges which is depend upon depreciation. Now uh, tariffs are also divided into different parts. One of them is your two part. You can see that high threshold level for recovery of fixed charges is not in line with the basic concept of the two part tariff. High threshold level of 80% is justified only in single part tariff. Performance level for recovery of fixed charges. So if you are operating PLF, availability in the country has gradually improved and has reached a level of 72% during the year 2002 to 2003. So considering average backing down of about 2%, national average PLF plus 2% can be adopted as target availability norm for recovery of fixed charges. So there are some norms which is used for the tariff or depreciation. So high norms for target availability possesses significant list of generating stations for non-recovery of fixed charges, mitigation such as risk. Following is proposed for kind consideration of the commission. So cumulative availability for the total tariff period may be considered instead of the present practice of annual availability so that non-recovery of fixed charges in any particular year can be compensated by improved availability in the subsequent years. So drawal schedules of the beneficiaries may be limited to generation corresponding to target availability and generation beyond this may be allowed for trading direct or power supply. Trading in a availability may be considered that is a station which is unable to achieve target availability level can purchase capacity from other stations to offset its deficit. Incentive disincentive may be provided on equitable basis. So incentive on availability. The concept of availability based tariff as finalized in the NTF provided for incentive on availability of the station. This was envisaged to incentives generators for making the units available to meet the requirement of the grid. So providing incentive based on availability will also ensure the actual generation of the station is not PLF driven, which was earlier the practice and had resulted in wide frequency variation. So at present, SEBs are giving schedules considering variable cost plus incentive, which is distorting merit order operation. So incentive on availability will promote merit order operation. So furthermore, declaring the availability of the station generator has to make all arrangements for availability of fuel, equipments, manpower, etc. PLF from the station thereafter depends on the schedules given by the beneficiary. So in view of the above, under availability based tariff, incentive should be linked to the availability of the station and not on PLF. So, uh, depreciation is very important part in to uh, for the tariff. And tariff is the charges which is taken from the consumer, how much electricity it is utilizing. So day by day, the charges of tariff are increasing because there are some amendment in the rules of grid and generating power plants. factor. Okay, so it is the ratio of average load to the maximum for a certain period of time. This is your load factor. The load factor is called daily load factor if the period of time is a day, and if the period of time is a month, then this is called your monthly load factor. Similarly, if the period of time is your year, then this is called your yearly load factor. Because your average load is calculated for your daily basis, monthly basis, and yearly basis, right? So, the we have done about connected load, maximum demand, and your average load. So the load factor is the ratio of your maximum load is divided by average load. So this is your load factor. The formula for this load factor is equal to average load is divided by maximum demand. If the plant is in operation for T hours, suppose your plant is operating for T hours, then the load factor will be average load into divided by T upon maximum demand into T divided by T. So unit generated in T hours and maximum demand into T hours. We will discuss it in a numerical, so you will be able to understand it easily. Now next is your the load factor may be daily load factor, monthly load factor, and annual load factor. If the time period considered in a day, that is a daily load factor. If the time period is considered for a month, that is your monthly, and if time period is considered for a year, that is your yearly load. So load factor is always less than 1. Why? Why is it so? Because you have seen the formula that load factor is always equal to average load upon maximum demand. And maximum demand is always greater than your average load. Okay. For example, mm, in your house that you have connected 4 bulbs, which is your 100 watts. So total load is your 400 watt, and you are connecting a fan that is your that is also your 100 watt. So total load is your 500 watt. At a time, you if you want to calculate the average load of this, then you have to suppose you are using uh, 20 megawatt for 1 hour, and sorry, 100 watt for 1 hour, 200 watt for next 3 hours. Then you will calculate the average load. When you will divide this average load by maximum demand, suppose you are 200 megawatt, 200 watt, then the load factor is always less than 1. So the average load is always smaller than your maximum. So the load factor plays a key role in determining the overall cost per unit generated. Higher the load factor of the power station, lesser will be the cost per unit generated. If your average load is always less than, it is always minimum, then the load factor will always be less than 1. If you are your average load is high and maximum demand is less, then you will get a higher load factor. Higher the load factor of the power station, lesser will be the cost per unit generated. Now, the important point is your diversity factor. So, diversity factor is the ratio of the sum of individual maximum demands. Actually, there are different consumers. So, we have to calculate the maximum demand of different load. Then we will divide this demand factor. We will we will calculate the maximum demand of different loads, and the sum ratio of the sum of individual maximum demand is divided by maximum demand of the power station is known as diversity factor. So a power station supplies load to various types of consumers whose maximum demand is different. Generally, do not occur at the same time. Suppose there are four houses, so maximum demand of that four houses will be different, and it will be different at different time. Okay, so the maximum demand generally do not occur at the same time. Therefore, the maximum demand do not occur at the same time. What you have to do, the uh, therefore the maximum demand on the power station is always less than the sum of individual maximum demand of the consumer. For example, a power station which is connected to the four consumers. One consumer having his maximum demand at a different time. Second consumer will have his maximum demand at different time. Third consumer also will have his maximum demand at different time. Fourth consumer will have his maximum demand at different time. But the power station maximum demand will be different. Okay, so therefore the maximum demand on the power station is always less than the sum of individual maximum demand of the consumer. So diversity factor will always be greater than to the one. So load factor is always less than one because the formula of load factor is equal to average load upon maximum demand, and average load is always less than to the maximum demand of a particular consumer. But diversity factor, actually you can differentiate these two, that load factor you are calculating for a particular consumer, but diversity factor you are calculating for a group. Okay, so load factor is always less than 1 and diversity factor will be always greater than 1 because it is the ratio of demand in individual maximum demand which is divided by the maximum demand of power plant. So diversity factor is always greater than 1. The greater the diversity factor, the lesser is the cost of generation of the power plant. So the formula for diversity factor is equal to sum of individual maximum demand is divided by maximum demand on power plant, which is in kilowatt. Now next come to the point which is very important, plant capacity factor. So it is the ratio of actual energy produced to the maximum possible energy that could have been produced during a given period. So formula for plant capacity factor is equal to actual energy produced and maximum energy that could have been produced. Suppose a plant has its capacity to producing suppose 500 megawatt, but it is producing 400 megawatt. Okay, so 400 megawatt is divided by maximum 500 megawatt. So this define the plant capacity factor. So another formula for plant capacity factor is equal to average demand upon plant capacity. Okay. So if the considered period is 1 year, so annual plant capacity is equal to annual kilowatt hour output upon plant capacity into 8760, which is hours in a year. Okay. So basically, you can define that the plant capacity, like the rated capacity of a plant is suppose 500 megawatt, but it is using only 400. It is producing only 400 megawatt. So this is your plant capacity factor. So the plant capacity factor is an indication of the reserve capacity of the plant. A power station is so designed that it has some reserve capacity for meeting the increased load demand in future. So we have seen that the day by day your energy demand is increasing. So it is not possible to set up a plant again from zero. So we have to take some reserve capacity for our future planning. Okay, so it has some uh, future reserve capacity, and future demand can be calculated by your forecasting methods, load forecasting methods. So that is a different topic. We will discuss it on next unit. So it has some reserve capacity for meeting the increased load demand in future. So therefore, the installed capacity of the plant is always somewhat greater than the maximum demand on the plant. So reserve capacity can be defined as plant capacity minus maximum demand. Okay. So it is interesting to note that the difference between load factor and plant capacity factor is an indication of reserve capacity. Uh, so if the maximum demand on the plant is equal to the plant capacity, then load factor and plant capacity factor will have the same value. So in such a case, the plant will have no reserve capacity. So this is very important point. So now we have discussed about our average load, maximum demand, your load factor, your diversity factor, and your reserve capacity. Hope you are able to differentiate between these particular definitions. Now, next is your plant use factor, which is equal to station output in kilowatt hour divided by plant capacity into hours of use. Next, we come to the next point. The utilization factor or use factor is the ratio of time that a piece of equipment is in use to the total time that it could be in use. So it is often averaged over time in the definition such that the ratio becomes the amount of energy used divided by the maximum possible to be used. We will take an example by which you will be able to understand the utilization factor, and uh, the formula for utilization factor is equal to maximum demand kilowatt divided by installed capacity. For example, if a plant has a maximum demand is kilowatt in suppose 100 megawatt, 100 kilowatt, and its installed capacity is 200 kilowatt. So 100 is divided by 200, that is always less than 1. Okay. So like this, we can easily calculate the utilization factor. Now, diversity factor is commonly used, this is your diversity factor we have already done, but again we can see because it is very important. So diversity factor is commonly used for a complete coordination study for a system, because you have seen in that our previous slide that yes, diversity factor you can see by this formula sum of individual maximum demand, and this is divided by maximum demand on power plant. If you are able to find out your diversity factor, like different user which using maximum demand at different time, if you are able to calculate this diversity factor, uh, uh, then diversity factor you will be able to coordinate a study for a system, and this diversity factor is used to estimate the load of a particular node in the system. So diversity factor can be used to estimate the total load required for a facility or to size the transformer. If you are able to calculate diversity factor very effectively, then you can easily find out that which size of transformer you required at a particular node. So it is very important. Now we come to the example. So from the example is a generation station of 1 megawatt supplied a region which has the following demands, uh, from midnight to 5 a.m. 5 a.m. to 6 p.m. it is no load requirement. 6 p.m. to 7 p.m. it is 800 kilowatt load requirement. 7 p.m. to 9 p.m. it is required 900 kilowatt. 9 p.m. to midnight it requires 400 kilowatt. So uh, what you have to do first, you have to draw the daily load curve and the load duration curve, which we have already drawn in our previous lecture. And the second point is you have to find the load factor, the reserve capacity, the plant capacity factor, and plant use factor, and the hours that the plant has been off and utilization factor. So we will discuss the second point in this lecture. Now, when the transmission line losses are neglected, in this calculation we will neglect the transmission losses. So generation is equal to the demand, okay, and the demand is equal to load, okay. So installed capacity is 1 megawatt, like 1000 kilowatt, and maximum load is your 900 kilowatt, which is already given, that the generating station of 1 megawatt. So 1 megawatt is its installed capacity of power plant. Okay, it can generate 1 megawatt electricity or 1 megawatt energy, 1 megawatt of power. Okay, so power generation of this power plant is 1 megawatt. Now, 1 megawatt can be written as 1000 kilowatt, and from the table you can see that the maximum demand is your 900 kilowatt. So the maximum demand is your 900 kilowatt. So the average load is equal to area under the load curve, okay, which is we, which is the formula of average load. That is area under the load curve, kilowatt hour and number of hours. Okay, when you will draw the graph of load duration curve, you can easily find out this, and you can see here that from midnight to 5 a.m. Okay, so it is 5 hours. You are using 100 kilowatt power. So 5 into 100, this is your 500, plus for next 13 hours. Okay, there is no load, 5 a.m. to 6 p.m. There is no load. This is your 12 hours, 13 hours, which is divided in multiply by 0. Then for 1 hour you are using 800 kilowatt. So 1 into 800 kilowatt. Then you are using 900 kilowatt for 2 hours. So 2 is multiplied by 900. Then 3 for 3 hours you are using 400. So your load which you are using for a particular time period is over here. This can be calculated by under area under the load curve. So you can see that uh, the uh, total load demand is this, and this is divided by 24. So you will get that the average load is your 179.16 kilowatt for a day. Okay. This load it is your average load for a day. Now this is your load curve and this is your load duration curve. Now we have to calculate load factor. So you know the formula of load factor, which is your average load upon maximum demand, and the load factor must will always be less than 1. So average load will never be greater than your maximum demand. You can see from this formula that the average load is not higher than your maximum demand. So your maximum demand for this question is 900, and your average load is your 179.16 kilowatt. So you can easily calculate the load factor, which is equal to average load upon maximum load, and average load is your 179.16 kilowatt, which is divided by 900 kilowatt, and the load factor is your 0.199, and if you calculate it in the percentage, then it will be 19.19% load factor. Okay, now we come to the next point, that is your reserve capacity. So we have already done in our previous slide that reserve capacity formula is installed capacity minus maximum demand, and the installed capacity of the power plant is 1 megawatt. Okay, and the maximum demand is your 900 kilowatt. So 1 megawatt can be converted into kilowatt, that is your 1000 kilowatt minus 900 kilowatt, it is 100 kilowatt. So the reserve capacity is equal to installed capacity minus maximum demand. Suppose your installed capacity and maximum demand are same, that there will be no reserve capacity. Is it clear? Now, next we come to the plant capacity factor. So average demand is your 179.16 kilowatt from this power plant, and installed capacity is your 1 megawatt. So what is your plant capacity factor? It is your 17.91%. So the plant we are using, which has the capacity of 1 megawatt, is not fully utilized. Plant use factor. The formula for plant use factor is actual energy produced in kilowatt hour divided by plant capacity into number of hours. So you can calculate this from that your average load is 4300 kilowatt hour. Okay, so actual energy production is 4300 kilowatt hour, and your plant capacity factor is your 1000 kilowatt hour, and number of hours which is you are using this load, you can see that this average load is utilizing 1 2 3 4 5, and this is your 6 hours. Okay, so 5 1 2 3 4 5 5 hours, and this is your 6 7 8 9 6 7 8 6 7 8 9 10 and 11. So total hours is your 11 hours. So this load is utilizing for 11 hours. So the plant use factor is equal to 39.09%, and your plant capacity factor is your 17.91%, and plant use factor is your 39.09%. Now we come to the utilization factor, which is your maximum demand upon installed capacity. So utilization factor is your 90%. You are not utilizing this power plant at 100%. That's why you are getting reserving capacity of 100 kilowatt. Okay. So by using these calculation, you can easily calculate you can easily calculate the load factor, utilization factor, and plant use factor, maximum demand, and average load. Now we come to the next point, next question, that, for example, a generation station has a maximum demand of 20 megawatt, a load factor of 60%, plant capacity factor is 48%, and plant use factor of 80%. Actually, in this question, the maximum demand is given, the load factor is given, plant capacity factor is given, and plant use factor is also given. So you have to calculate the daily energy produced, that how much energy it is producing in kilowatt hour, the reserve capacity, which is your plant. capacity minus maximum demand. So you have to calculate maximum demand also. Then the number of operating hours per daily and the maximum energy that could be produced daily if the generating station was running all the time. Okay, so this is very important example. For the solution, we come to this point that find the daily energy produced. So load factor is given. So what is the formula of load factor? Which is equal to your average load divided by maximum demand, maximum load. So average load, first we have to calculate the average load. Load factor is your 60%. So this is your 0.6 is equal to average load or divided by 20 megawatt, and 20 megawatt is your maximum demand, which is given in the question. So you can easily calculate that your average load, which is 12 megawatt. What is the formula of average load? Area under the load curve upon number of hours. In so the number of hours is 24 hours, and average load, average and area under the load in kilowatt hour means this is the energy which is generating, this is the energy which is producing. So 12 multiplied by 24, this is your 288 megawatt hour. Now this is your energy producing through the power plant. Now find the reserve capacity. So first you have to find out its installed capacity. So installed capacity can be easily calculated through plant capacity factor, which is equal to average demand upon installed capacity. So installed capacity is equal to average demand upon plant capacity factor, which is already given or we have calculated. So this is equal to 25 megawatt. Now we come to the next point. This is your reserve capacity. So installed capacity of plant is at 25 megawatt, and the maximum demand is already given in the question, which is your 20 megawatt. So reserve capacity is equal to 5 megawatt. The third part of this question is you have to calculate, find the number of operating hours per daily. So plant use factor is equal to average demand into time divided by installed capacity into number of operating hours. So from this formula, you can easily calculate the number of operating hours. 0.8 is equal to 12 into 24 divided by 25 into number of operating hours, and number of operating hours is equal to 12 into 24 divided by 25 into 0.8. This is equal to 14.4 hours. So this is all about this lecture, and I think you are able to calculate your load factor, your diversity factor, and your maximum demand and average load, plant capacity factor. Okay, now these are some questions which is based on your previous and this lecture. So what is the advantage of sectionalizing of power plant? That is that you can get high reliability electrical energy, which is very important. The area under the load curve represent the average load on power system, maximum demand, numbers of unit generated, or load factor. So the area under the load curve uh, is represented by is always represented the energy which is producing from your power plant, and in power plant the energy which is producing is always calculated in the term of units. So this is your number of units generated. So the right answer for this question is C. Next, which of the following is equal to the maximum demand? So the ratio of area under curve to the total area of the rectangle, the ratio of area under curve and number of hours, the peak of the load curve, the area under the curve. You can easily calculate maximum demand, that will be your peak hours. Okay, now load duration curve indicates the variation of load during different hours of the day, total number of units generated for the given demand, total energy consumed in by the load, the number of hours for which the particular load lasts during the day. So it always shows that the load during different hours of the day. Which of the following is called as cold reserve? Reserved capacity available but not ready to use is always called a cold reserve. Now, coincidence factor is reciprocal of actually coincidence factor. We will discuss it in the next lecture. Now, in practice, what is the value of diversity factor? So you have seen in your previous slides that I have already explained the formula of diversity factor. So diversity factor is always greater than 1, and you can see that because it is the sum of individual demand and just a wait. Yes, it is equal to sum of individual maximum demand and divided by maximum demand of the power station. So it will always be greater than 1. Okay. Now, the right answer for this question is it will always be greater than unity. It will not be less than unity. It will not equal to or greater than unity. It will not less than 0. It will always be greater than unity. Now the load factor is, we have already done, the load factor is equal to average load is divided by maximum demand, and average load is always less than your maximum demand. So load factor is always less than 1. So always less than unity, less than or greater than unity, always greater than 1, and less than 0. So the this will be always less than 1. So A is the right answer for this question. Now we come to the next point. What is demand factor? So we have already discussed about your demand factor. So ratio of connected load to maximum demand, ratio of average load to connected load, and ratio of maximum demand to the connected load, ratio of kilowatt hour consumed to 24 hours. So you can easily find out the answer for this demand factor. Now, next question is your size and cost of installation depends upon your maximum demand. The reference of this lecture is Generation of Electrical Power by B.R. Gupta and NPTEL. By going through these references, you can easily understand the load factor, load duration curve, and utilization factor, reserve capacity, and your mass curve, chronological curve. So you can easily understand by this by these book or some NPTEL lectures. So this is all about your uh, load duration curve, by which you can easily understand the different factors which is important for your power generation plant. Thank you.